Hi, everybody. Welcome to topic number 20, binomial distribution. So this is a very, very specific type of distribution. So what is so-called a binomial probability distribution? It's a very specific type of discrete probability distribution. So last time in topic 19, I began to introduce the concept of the wording distribution or probability distribution. All right, so here is a very specific example. It's called the discrete probability distribution, which is a binomial distribution. So properties of a binomial distribution. Okay, for this type of distribution, the experiment consists of a fixed number and lowercase n number of identical trials. Each trial is independent of the others. For each trial, there are only two possible outcomes. That's what's so unique about this. Okay, success and failure. Okay, is a discrete probability distribution because we can count. We can count the number of success. We can count the number of failures. Okay, there's no in between. Continuous random variable will be, will be something where it's a little bit different type of distribution as compared to the binomial probability distribution, which is something we got to count. Okay, it's not like it's not like measuring rainfall, things like that, where we can get, so many decimal of, inches. Okay, when it comes to counting success and failure, those are integers. Those are whole numbers, something that are countable. All right, so there are only two possible outcomes called success and failure. The probability of success is denoted as lowercase p. The probability of failure is denoted as q, or sometimes we can say 1 minus p. Okay, 1 means 100% minus the probability of success. That will be probability of failure. Most of the time, I just denote them as q. The binomial random variable, capital letter X, will count the number of success in n number trials. For binomial distribution, to find the mean, okay, is always a number of trial times probability of success. That will actually give you the mean of the distribution. For variance, will be sigma squared, which is equal to n, the number of trial times probability of success times probability of failure. Okay, that will give you the variance. So we talked about variance and standard deviation before. So if you want to find the standard deviation, you just take a square root of NP and Q. So here's an example, kind of help you understand, how to calculate this binomial distribution. So let's say Mr. Chen is a 75% free throw shooter. Find the probability of Mr. Chen making exactly 3 out of 5 free throws. Exactly 3 out of 5. Okay, so let's think about this. 5 free throws. 1, 2, 3, 4, 5. Let's say I make the first one, I miss the second one, I make the third one, and I make the fourth one. Exactly 3, and I miss the second and the fifth shot. Okay. So each time I make my free throw, it's a 75% chance I make them. So that means the time I missed, the probability of missing a failure is 0.25. So if you think about it, one task followed by the other, my probability of making exactly 3 out of 5 got to be 0.75 times itself 3 times, which is to the third power, times my probability of missing, which is 0.25 to the second power, right? One task followed by the other, we multiply all of them. So when we multiply all of them, same number 3 times, this means to the third power. So this is my probability of making exactly 3 out of 5. But this is only one way. This is only one way for me to make exactly 3 out of 5 shots. I could actually miss the first one, make the second, third, and fourth. So that would be another way. So we need to actually count the number of ways that I can make exactly 3 out of 5 free throw. So this is a probability of just one way. Okay, so we need to count the total number of ways. So we need to multiply the probability my probability of making exactly 3 out of 5 free throw for one way times by the total number of ways. So the total number of way will be, there are 5 free throws, right? I'm shooting 5 free throws, choosing making 3 of them using combination, because it doesn't matter which make, the order of which make does not matter. Okay, so this will give me, so this part will give me the number of ways making exactly 3 free throws. And the second part I wrote is actually telling me the probability of making my free throws. Okay, this gives me a probability of failure. So that is actually what the formula here is trying to indicate. For a probability for a binomial distribution, for a binomial random variable x, the probability of obtaining x number of success in n independent trial is given by n choosing x, right? So many ways of success times probability of success times by x number of success times 1 minus p, which is your q, right? The number of failure and raising to the n minus x. So that will be the number of failure. X is the number of success, n minus x will be the number of failure. P is the probability of success, Q will be the probability of failure. Okay, so that's the formula to actually find the probability of making exactly 3 out of 5 free throws. Okay, so that's a binomial distribution. You know it's a binomial distribution because you only get 2 outcomes, success and failure. So a lot of examples that a couple of examples we're going to do in a minute will actually make it sounds like that. So you can kind of learn, you can kind of see how binomial distribution is being identified. All right, I put this right here, how to read probability questions. So I kind of been highlighting them throughout the semester. So here I'm actually making a little list. Okay, the phrase that is at least, no more, less than, or greater than, equal to is using this mathematical symbols: greater than or equal to. More than, greater than, there's no equal. Less than, fewer than is less than. I will use this symbol. No more than or at most is less than or equal to. Exact, equal, is, I'm using equal sign, because it does matter what symbols I use. Okay, it does matter what symbol I'm going to start using. So before I show you the calculator, how to do this problem in a calculator, the binomial distribution calculator, I want to introduce this 2 concept: CDF versus PDF. CDF stands for cumulative distribution function. It can easily be used for computing probability involving with less than or equal to. Cumulative distribution function is involving with less than or equal to. The word cumulative distribution, the word cumulative, we actually learned that word a long time ago. I think, see if I remember correctly, it was beginning of the semester when we talk about the word frequency, which is topic number 5, something called cumulative frequency. Cumulative frequency means we will add it up. So if I go to topic number 5, kind of just give you an example. All right, this is topic number 5. See this cumulative frequencies that on the notes that we took. So to find cumulative frequency, we take, the frequency of first class was 3. So for the cumulative frequency of the next class, we will take the frequency of the second class plus the frequency of the first class, and so on and so forth, right? For the frequency for the third class is 2. So the cumulative frequency for this third class will be 2 plus the 5. It accumulates all the way up to the total 21. Okay, so that's what's going on here with the cumulative distribution function. It involved with the wording less than or less than equal to. Okay, it's actually accumulating from 0 all the way up to what we, the random variable x that we want to compute. PDF stands for probability density function. Okay, we will use PDF for computing probability involving with exact. Okay, so how to find binomial CDF and PDF? Okay, we will actually go to second bars, which is looking for the word distribution. And we will actually either choose CDF or PDF, depends on the probability questions. And what we're gonna enter inside the PDF or CDF is NPX. N is number of trials, P is a probability of success, and X is a number of success. So this example, okay, is using equal sign. So using equal sign, that means I'm gonna use PDF. So for this binomial distribution, okay, involving with equal sign, I'm gonna write it out the distribution, okay? I'm gonna write this out. I'm gonna write out what I'm going to put in the calculator. So I'm gonna pick binomial PDF, probability density function. And what I put inside the parenthesis here in a minute is gonna be N is 8, right? 8 trials. P is stand for probability of success, which is 0.5, comma, and the number of success, okay? X is 6. The number of success is equal to 6. All right, let's use our calculator to find this answer. We're gonna run to 4 decimal places. Probability always run to 4 decimal places. So here, press second in the word forest or looking for the word distribute. Go down until you find binomial PDF. I'm trying to find the probability of exactly 6 success for binomial distribution. Binomial PDF. All right. And I'm going to type in 8, comma, 0.5, comma, probability of success is 6. So exactly 6 success out of 8 independent trials with a 0.5 success, probability of success, okay, it will only be 0.1094. The probability of exactly 6. It's not from 0 to 6. Okay, it's actually from, it's just 6. 0.1093. 94, excuse me, round to 4 decimal places. So if I go back up here to this same problem I wrote down about Mr. Chen shooting a 75 shooting free throws. All right, the question asking what's the probability of Mr. Chen making exactly 3 out of 5 free throws. So that means it's a binomial PDF. Right, exact means equal to 3 free throw out of 5. So the number of trials is 5, shooting 5 times, comma, my probability of making a free throw is 0.75, comma, the number of success I want in this example is exactly 3 out of 5, 3 shots. So the chance of the probability of me making 3 out of 5 free throws, even though I'm a 75% free throw shooter, is actually 0.2637. Kind of weird question, kind of weird to think about it. Okay, so one of the most famous free throw shooter is actually Shaquille O'Neal. Shaq can barely make a free throw. So if we assume Shaq, well, let's say Shaq is a 50% free throw shooter at the end of the season. Okay. Or at any given time, his previous stat shows he's a 0.5% free throw shooter, right? So what's the probability that he makes both free throw on the next time he go up there? Okay, so think about it. If Shaq is gonna shoot if we know Shaq is a 0.5, 50% free throw shooter, all right, so now he got foul, step out to the line, right? And he's gonna shoot 2 free throws. So the probability, so the number of tries is 2, probability of success is 0.5. So what's the chance of him making the next 2 free throw? It's only 0.25%. It's kind of weird, right? Even though he is a 50% free throw shooter, but the probability of him making the next two, okay, exactly two, is only 25% chance. Okay, that's the way how we actually think about the binomial distribution. So even though I was a 75% free throw shooter, but I'm not asking to find the probability of making all five of them. I'm only asking the probability of making three of them out of the five. All right, let's try another example, okay? So this one is less than. This one is less than. So when we involving with less than, that means, what that means is the probability I'm trying to look for is 0, 1, 2, all the way up to 3. I want my probability of success is less than 4. So that means 4 is not one of my success. Is 0, 1, 2, and 3 that together I'm looking for. So this is where we will use the CDF, cumulative density function. Cumulative means the calculator will automatically take the probability of 0. It's basically taking the probability of this one plus the 1 success plus the 2 success plus the 3 success. You will actually do all 4 computation together, okay, under the CDF. So this is binomial CDF cumulative density function, because I want the calculator to accumulating all the probability of each one all the way up to 3, because I'm looking for probability that's less than 4. So n is 6. Probability of success is 0.7, comma, the number of success I want to add up to is only a 3, not 4, because I'm not including 4. So second vars or distribute, go down. And your calculator might look a little bit different than mine. If you have a newer version calculator, it will tell you you need to type in the trials, success, and the X and paste. But eventually it will look similar to what you see here. Okay, it will look just like what I'm about to type in, 6, comma, 0.7 or 0.7, either way, comma, number of success is only a 3. So probability, okay, so the probability altogether, the 0, the 1, the 2, the 3, all right, add up together equal to 0.2557. So rather than do PDF of each one, then add them all up, the CDF can allow me to, allows the calculator basically add up 0, 1, 2, and 3 together for me to get my answer. All right, greater than equal to 17. Okay, so cumulative density function, the number of success is greater than equal to 17 out of 18 trials. So that means if I'm start counting, right, greater than equal to 17 out of 18 trial, this 0, 1, 2, 3, all the way up to 16, 17, 18. This is the total. So what I want, this is where the complement rule comes in. The probability that I want is greater than equal to 17. So that's only referring to 17 and 18. So when we put, so think about this. If I use the binomial CDF, okay, it will actually calculate the probability from 0 all the way up to 16. If I put 16 for the number of success. But that's not what I want. What I want is 17, 18. So what I don't want is 0 all the way to 16. So n is 18, probability of success is 0.9. Number of success, if I put 16 right here, this tells me exactly what I don't want. So to find probability of what I want, we can use a complement rule, which is take 100% minus probability of what I don't want. Okay, 1 minus probability of what I don't want will equal to what I want. So this is where, some of the topic we went through about probability comes back in, some of those techniques, the complement rules can be very useful here. So CDF is accumulating my probability from 0 all the way up to 16, which is what I don't want. because this problem want me to find the probability that is greater than or equal to 17. So that means probability of 17 and probability of 18. All right, let's put this in the calculator. 1 minus binomial distribution. Let's go down to find the CDF. All right, 18 is number of trials, comma, 0.9, comma, 16, right? From 0, so this 16 means from 0 all the way to 16, what I don't want. 1 minus that will give me the probability that I want, which is 0.4503. Okay, so those examples are practicing how to use a calculator. Let's do an actual application. So a certain insecticide kills 70% of all insects in the laboratory experiment. So this thing can kill 70% of all the insects. A sample of 8 insects is exposed to the insecticide in a particular experiment. What is the probability that no insect will survive? See, this is a little tricky on wording. Some of the question we are going to see is a little bit tricky. Okay, so it kills 70% of it. Okay, but the way how the question is asking is, what's the probability that no insect will survive? So if the kill rate is at 70%, that means the survival rate got to be at 0.3. It's 30%. So the probability of success, P, got to equal to 0.3, because the question is using this wording, survive, right? Number of trials, N, is equal to 8. Probability of surviving is 0.3. List a number of success. Well, no insect will survive. So that means probability of success is equal to 0. Let me write it this way. The probability that I'm looking for, random variable X, is equal to 0. Okay, so here you can just, when you enter this answer, when you enter a problem like, answer like this in the graphical equation, you will have to use a subscript and put it equal to 0. All right, write out the computation of binomial distribution above. So this is actually no insect will survive. So that means exactly 0 will survive. So that's binomial PDF. Number of trials 8. Probability of survive is 0.3. The number of survive I'm looking for is 0. Okay, so now let's punch it in. And you can actually, if you want to find out what's the probability that 1 will survive, you just put a 1 here instead of 0. Okay, that's basically the idea. How you actually find the answer. Now think about it. Insecticide either kill or don't kill, right? So that's your success and failure. Either you survive or don't survive. So that's where the binomial part comes in. 2 outcomes, success and failure. All right, 8, comma, 0.3, comma, 0 will survive. 0.0576, that's a probability. So the probability, so if you actually move the decimal to the right 2 places, this is about 5.76% chance that none of them will survive. So that's a very interesting answer, because what is a chance that 8 of them, none of them will survive? It's only a 5% chance that none of them, almost 6% chance none of them will survive, because the kill rate is only at 70%. Okay, so that's why a lot of the time insecticide doesn't kill all the insects. But think about it though, if you have something that can kill all the insects, that's actually not a good thing. I know at home, we want to kill all the bugs, all the insects that come to the house. But if you have something that's strong that can kill all the insects, that's probably gonna kill yourself too. Okay, so that's why these insecticides is not 100% kill rate. If it's 100% kill rate, that's a very dangerous thing to have in the house. All right, a quality control inspector has drawn a sample of 17 light bulbs from a recent production lot. If the number of defective light bulb is 1 or less, right? Light bulbs, either defective or not defective. If the number of defective light bulb is 1 or less, then the lot passes the inspection. So suppose 30% of the light bulb in the lot are defective. So it is known 30% of 30% in 30% of bulbs produced in the lot are defective. What is the probability of that the lot will pass the inspection? So think about this, passing the inspection in the right up here, it says to pass the inspection, the number of defective light bulb is 1 or less. All right, to pass it, it gotta be 1 or less defective. And the problem you're giving me, this number right here does means defective. Okay, so my probability of success, which implies here means defective light bulbs, is 0.3, 30%. The number of trial N is 17. Okay, think about this. Passing the inspection means 1 or less defective bulbs. So we need to know the probability of defective bulbs, which is 30%. Okay, because we need to, because that's the way how the way it worded. It's kind of strange if you really think about it. Okay, so probability of success really implies for this example is about probability of selecting a what? A defective bulb, defective light bulbs. There's a number of success. Oh, this is tricky. To pass, gotta be 1 or less, right? 1 or less. So that means my probability of the random variable X defective bulbs gotta be less than or equal to 1. Gotta be less than equal to 1. 1 or less means less than equal to 1. So that means I'm looking for the probability 0 and 1, right? So this is gonna be binomial CDF. Number of trial is 17, probability of success is 0.3, and I need to compute my probability up to 1, right? Which is 0 and 1. There you go. All right, close parenthesis. All right, let's punch it in the calculator and see what we got. Binomial CDF. All right, which is B, alpha B. See, alpha B will give me that. 17, comma, 0.3, comma, 1. 1 defective. Well, excuse me, 1 or less defective, excuse me. So I'm only compute up to 1. All right, so probability to pass the inspection is only 0.0193. Okay, all right, let's look at some homework. Okay, what are the 2 possible outcomes for the binomial distribution? So that will be success and failure. All right, enter the formula for mean and variance of a binomial distribution. So that will be up here. So please enter using graphical equation. This is on first page. All right. So mean and variance. So tapping these for number 2. All right. For binomial distribution, probability of success denoted as which one? Okay, so this is multiple choice. All right, assume the random variable X is a binomial distribution. So this is very similar to what I showed you earlier. Enter the computation inside the box below. Okay, so this is less than or equal to 1. So that means we only want to compute up to 1. All right, and number 2, find the probability, round to 4 decimal place. This is the same problem. 60% kill rates, 7 insect exposed. So this one is asking exactly 4 insect will survive. Okay, exactly 4 will survive. So that's your number of success. So 5 different steps. Okay, last one, run the answer to 4 decimal place. Okay, question number 6 is the same thing as one I just did about the light bulbs. Okay, if the number of defective bulb is 2 or less, it passes the inspection. So I'll give you the same exact probability of defective 30%. This time I'm looking for 2 or less instead of 1 or less. All right, so follow the step I just show you. Okay, when you enter into the homework. So just real quick, showing you what it means what the wording binomial probability distribution means, which is about probability success and failure. Okay, so this is actually our first official probability distribution that introduced in this class. So in the next couple topic, I will introduce another key important distribution, which we will use that same distribution throughout basically rest of the semester. All right, thank you for watching.